Intuitively, we said a function f from R to R is continuous if it mapped nearby points to nearby points. And we captured this intuition in the following precise manner. We said the function is continuous at a point A if and only if for every epsilon greater than 0, there exists a delta greater than 0 such that whenever mod of x minus a is less than delta, mod of f of x minus f of a is less than epsilon. And the relationship between the intuition and this precise notion is that modulus kind of acts as a distance. Now, this idea can be used to define continuity for functions from Rn to Rm. Why? Because now we know that norm is a form of distance on Rn. Thus, we can say that a function f from Rn to Rm is continuous at a point A if and only if for every epsilon greater than 0, there exists a delta greater than 0 such that norm of x minus a is less than delta implies that norm of f of x minus f of a is less than epsilon. So now we have an abstract definition that matches with our intuition. However, this definition is a bit unwieldy. Why? Because here x and a are elements in Rn and f of x and f of a are elements in Rm. They are not numbers. Further, this norm itself is a bit complicated. So, in some sense, this definition is not so useful. But recall that f can be expressed in terms of m functions f1 to fm. So if we can express continuity of f in terms of these component functions, then it will be easier to understand continuous functions. And that's exactly what we are going to do. We will show that f is continuous if and only if fi is continuous for all I. And it should not be too surprising because it's a direct consequence of the way in which we have defined now. So let's try to see a proof of this fact now. Notice that norm x square is equal to x1 square plus x2 square plus etc. up to xn square, which will be less than or equal to n times xi square if xi square is the biggest of x1 square etc. up to xn square. On the other hand, notice that this largest xi square itself will be less than or equal to norm x square. Therefore, we can write that maximum of xi square is less than or equal to norm x square, which is less than or equal to n times maximum of xi square. So by taking square roots, we get that maximum of mod xi is less than or equal to norm x, which is less than or equal to square root n times maximum of mod xi, where the maximum is taken over all I ranging between 1 and n. And this result can be used to prove the theorem that we wanted to prove. Namely that we can express the continuity of f in terms of fi. So let f from Rn to Rm be a function such that f of x is equal to f1 of x, f2 of x, etc. up to fm of x. Then notice that norm of f of x minus f of a is less than or equal to square root of n times maximum of 1 less than or equal to I less than or equal to n mod of fi of x minus fi of a. Similarly, we know that norm of f of x minus f of a is greater than or equal to maximum of 1 less than or equal to I less than or equal to n mod of fi of x minus fi of a. Thus, making this small will ensure that this is small. So, in particular, mod of fi of x minus fi of a will be small. Similarly, if you ensure that this is small, that is, mod of fi of x minus fi of a is small for all I, then we can ensure that this is small. Therefore, if f is continuous, given any epsilon, you can choose a delta such that whenever norm of x minus a is less than delta, norm of f of x minus f of a is less than epsilon. But that would ensure that mod of fi of x minus fi of a is also less than epsilon for the same delta. And this implies that fi are continuous for all I. On the other hand, if fi are continuous for all I, then given any epsilon, I can choose a delta such that whenever norm of x minus a is less than delta, mod of fi of x minus fi of a is less than epsilon by square root of a, which would ensure that norm of f of x minus f of a is less than epsilon. Thus, f is continuous. Therefore, we have proved the theorem that we wanted to prove. Let us repeat the theorem. Let f be a function from Rn to Rm. And let fi be equal to pi I composed with f, that is, fi are the component functions of f. Then, f is continuous if and only if all the component functions fi are continuous. Once we have this theorem, it enables us to come up with various examples of continuous functions from R to Rm. Why? Because we already know how continuous functions from R to R looks like. And the above theorem tells that once you know them, we know continuous functions from R to Rm also. So to begin with, let us look at an example of a function from R to R2 defined as f of x is equal to 3x square plus 2 comma x into sine x. As 3x square plus 2 and x sine x are both continuous, this function is continuous. Another example from R to R3 can be given by f of x is equal to x square minus 1 comma ex log x comma cos x into sin x. Once again, as all the component functions are continuous, this function is continuous. Now that we have seen some examples of continuous functions, let us look at an example of a discontinuous function. For that, we just have to ensure that one of the component functions are discontinuous. One example from R to R3 is given by f of x is equal to x comma x square comma signum of x. Recall that signum of x was the function defined to be equal to minus 1 if x is less than 0, equal to 0 if x is equal to 0, and 1 if x is greater than 0. This function is clearly discontinuous at x equal to 0, and therefore the function that we have defined from R to R3 should also be discontinuous. In this manner, we can construct enough examples of continuous and discontinuous functions from R to R, and for that the theorem was extremely beneficial. Let us now try to come up with some examples of continuous functions from Rn to Rm. Recall that the earlier theorem said that it is enough to consider the special case where m is equal to 1. And one of the most important class of examples is given by the projection function, namely pi I from Rn to R that takes the element x1, x2, etc. up to xn to the number xi. And we will prove the continuity of this function pi I using the definition of continuity. More precisely, given any epsilon greater than 0, we will construct a delta greater than 0 such that norm of x minus a is less than delta implies that norm of pi I of x minus pi I of a is less than epsilon. And in this case, it's easy because we can just take delta is equal to epsilon. Why? Because notice that norm of pi I of x minus pi I of a is equal to mod of xi minus ai. And we know that norm of x minus a is greater than mod of xi minus ai. So if norm of x minus a is less than delta, then mod of xi minus ai is also less than delta. Thus we can take delta and epsilon to be equal. Inspired by this example, we can ask the following question. Consider the function f from R2 to R defined as f of x1, x2 is equal to x1 plus x2. Is this function continuous? Intuition should tell you that it will be continuous. And notice that it is the sum of two functions, namely pi1 and pi2, and they are both continuous. Thus, if sum of continuous functions are continuous, then f will be continuous. And as you would expect, sum of continuous functions are indeed continuous. However, we have to wait a bit before we see a proof of this fact. And we can ask more such questions. For instance, we can ask the question, is the function f from Rn to R defined as f of x1 to xn is equal to sine of xi a continuous function? Intuition should tell you again that this is continuous. Why? Because it's a composition of two functions, sine and pi I, and both these functions are continuous. And our earlier experience in analysis tells us that composition of two continuous functions is continuous. And even here it will be true, but we will see the proof only later. Now, once we have seen both these ideas, we can combine them. For instance, we can look at the function f from R2 to R that is defined as f of x1, x2 is equal to x1 plus sine x2. Let us end this video with a final example. Consider a function f from R2 to R defined as f of x1, x2 is equal to x1 sine x2. This time f is a product of two continuous functions. So if we can show that product of two continuous functions is continuous, this function will be continuous. These examples illustrate that if we can prove that continuous functions from Rn to Rm satisfy the familiar properties of continuous functions from R to R, then we can construct a huge class of examples of functions from Rn to Rm. And we will do that in the next video.